We say hi to the YouTube world and nation. And I know that you already have stuff written here. Let's just just put this here. You don't have to write this, but just so we all understand what we're doing. So we were talking about graphing complex numbers, a plus bi, and we learned that that has a secondary form. That's complex form. What does trigonometric form look like? Yeah. R. Yes, very good. So we talked about going from that to that. And some of you guys who were seniors yesterday, you know, we did a couple problems like that. Juniors, you were in here as well. We talked a little bit about that. But we already went over these examples, converting from this to this. I told you if you can't do that, then today's going to be a rough one, right? But the good news is that even if you are still struggling with that process, you're going to see 3 examples where we do that again today, okay? So we really have 2 goals today, and that is to learn how to work with numbers that are in this form, trigonometric form, and we want to be able to multiply and divide them. That's goal number 1. And goal number 2, be able to raise them to a power. And just to kind of like preface your brain and kind of, you know, just look at the ridiculous piece that you're going to be doing. This one right here, 1 minus I to the 100th power. Jordan, if you were to do 1 minus I times 1 minus I, like you were to write it out 100 times and do that, how long? I need an estimate. How long do you think that it would take you to do that? You can use hours, days, weeks. You could use years if you so choose.
I'll say a year and a quarter.
A year and a quarter. Okay, we're saying 15 months. Okay, 15 months. And we did it during first hour. We did it in 4 minutes and 57 seconds. And in second hour, and then third hour we did 3 minutes and 36 seconds. So we're gonna show you how we can actually do that in an amazingly incredible fashion. Okay? You want to do it what? 2? You all right? You ready? Remember, it's got to be your pace. It can't be my pace. Okay? All right. So we got to kind of do that. Okay. So let's start to multiply and divide. Given 2 complex numbers, I have r sub 1 times cosine of theta sub 1 plus I sine of theta sub 1. So that's just trigonometric form of a complex number. That's one of them, and we're going to write down a second one. So z sub 2 is r sub 2 times the cosine of theta sub 2 plus I sine of theta sub 2. So all I've done is I've just written that we have 2 distinct trigonometric numbers here, okay? Everybody good? So our goal is to write a formula for the following. Z sub 1 times Z sub 2. So I want to take this thing here times this thing here. Okay? Anybody want to take a guess? What do you think we do to the R values? We do. Yep, we just like you're asked to multiply, we multiply. Yep, follows pretty intuitive. R sub 1 times R sub 2. So that's how you get the new radius out front. You just multiply the 2 together. Anybody want to guess what we do for the theta values?
Would we multiply just the theta together, not the cosine?
Good thought to multiply the thetas. We don't multiply them, we do something else. We're actually going to add them. We're going to add them. Theta sub 1 plus theta sub 2. Okay? We don't have time to go through the proof of why that works out, but it does happen that you add them, add these, and you multiply those. Yep. Sine is the same piece. Not too bad, right? So let's do one of the problems that you would have on your test, which it says given z sub 1 is this thing and z sub 2 is this thing, we want to find z sub 1 times z sub 2. It's okay. So you multiply the r values and you add the theta values. Okay? So if I take z sub 1 and I multiply z sub 2, what am I going to start with? 10. 2 times 5 is my 10. Times the cosine of, now what? How are we going to add our pi over 4 and our pi over 3? Common denominators. Okay, good. So you guys are already there. 3 pi over 12 plus 4 pi over 12, which is a total of 7 pi over 12. Yep. So once you make those common denominators, 7 pi over 12. Good. Same thing for sine. Excellent. I sine of 7 pi over 12. That's it. So, yeah, good, good. No, that was good. Are we okay with that? All right, so now that you've seen the formula for multiplication, let's see if you can think about what the formula for division would be. Anybody want to guess what I do for the R values?
Would you divide all the values actually?
We divide the R values, so R sub 1 over R sub 2. Allie, what do we do for the theta values then? We do subtract them. So theta sub 1 minus theta sub 2. It is plus in the middle. Thank you. Other people made that mistake. Nope. Please just note the difference. Multiplying and dividing, adding and subtracting. So now let's perform z sub 1 divided by z sub 2. 2 over 5. Cosine of, so we'll go over here, Kenny. You guys can see that we have pi over 4 minus pi over 3. So as we found the common denominators, 3 pi over 12 minus 4 pi over 12, negative pi over 12. It is not. We'll see. 1 hour had it, the other hour did not, but we cannot leave a negative angle. Do you remember what happens to the cosine of a negative angle? What? You go the other way? Yeah. Close. All right. So do you remember this sheet? Yeah. And at one point, hopefully this comes back to us. So remember sine of a negative. So Rachel will do your idea. Remember how you said it just goes the other way? So sine of a negative, the negative pops out front. But what happens to cosine of a negative? It vanishes because it's an even function. So this is an even function. It disappears. Odd functions, it pops out front. Okay? All right? So what you can just remember is that cosine and secant, as they're reciprocals, the negative disappears because they're even functions, whereas all the others, the negative just pops out front. So that was from your last unit. You do, again, get that sheet on the test, but that's an important thing to note for this, that you remember what to do with the negative. So 2 over 5, cosine of what? Pi over 12, and then what's going to happen here?
Negative I.
Yep, or minus I sine of pi over 12. Sure, that'll be fine too. Good? Not too bad? So just to be clear, within our formula is always just subtract the, well, I'm sorry. Did I write that? Yeah. Yeah, sorry, that was your question. So this part is never subtraction here. These parts are subtraction. Yep, should be subtraction. Okay, sorry about that. Good? All right, so that's really the easy part. But from that, we come up with the mathematician who kind of developed this piece. His name was DeMoivre's, and his theorem that he put forth was, well, suppose that we have a complex number of z is equal to r times the cosine of theta plus I sine of theta. What if we were to take that complex term and raise it to the nth power? Now, we've already laid the foundation for this. We should be able to anticipate what will happen, because if you take z to the nth, ZZ really likes this lesson, right? Okay, if you take z to the nth, you get z times z times z times z times z times z, right? N number of times. So that means you're going to have r times r times r times r times r times r. So it's going to be r to the nth power. Because we multiply r that many times. So if you're going to raise z to a power, just take r to that same power times the cosine. Now think about this. Is it theta times theta times theta times theta, or is it theta plus theta plus theta plus theta? So if you're adding up all the thetas, what are you going to get? N theta. Or theta times n. Good. We good? Yes.
Is it theta or theta?
Excellent. So that's the Greek way that we spell it, and it's T-H-E-T-A. Okay. Theta. Yep. The Greeks had one letter for those two, letters that we have. Nope. Nope. There you go. Theta. Am I not pronouncing it well enough?
Well, no, I just
The English
I
language.
heard you saying theta, but then I say theta, and I hear other people say theta, and then
Theta with an F?
yeah.
Theta.
I was really
Like
confused.
yes.
Okay.
It's no English language.
Okay. Got it. All right. No, that's all right. Thank you. Thank you for your clarification.
What? No, I'm the man. We have to put it in trigonometry.
Yes, exactly. So Kenny sees this next problem. So we want to do 3 of these. The first one is going to be the most cumbersome. Okay, so we're kind of getting our feet wet with using DeMoivre's theorem. But let's all understand, if we were to multiply this out 10 times, we very likely might make a mistake, right?
Yeah.
And not only would we make a mistake, it would take us a very, very, very long time. So what we could do instead is, instead of multiplying this out 10 times, we can use DeMoivre's theorem, which starts with placing it into trigonometric form. What do I need to do in order to place it in trigonometric form? What 2 things do I need to find? Find r, and then, yes, and theta. What is my formula for determining r? Square root of a squared plus b squared. So we have fractions, so make sure everybody's with us. What is 1/2 squared? Don't say 1. 4. So a 4th plus a 4th is a 1/2. And so we're going to leave it as a square root of a 1/2. Now I know that makes some of you feel uncomfortable because you're like, I have a square root of a fraction, but just leave it be for a little while, okay? Yes, let's just leave it for a little bit and we'll see what happens, okay? Because remember, we're gonna take that to a power, aren't we?
Oh yeah.
Yep. Yep. Okay, so then tangent of theta is equal to what? B divided by A. Where is tangent positive? First and third. How'd you know that? All students take calculus. Excellent. First and third quadrant. Are we working in the first quadrant or the third quadrant? Because that's where it plots. Excellent. Inverse tangent of 1 in your brains or on your calculator? The 45. Which is pi over 4. Excellent. So that's what we practiced the other day. We place it in trigonometric form. The trigonometric form is z equals root of 1/2 times the cosine of what? Pi over 4 plus I sine of pi over 4. Excellent. So that's what z is. We started off by that. Now, without a doubt, you guys get to this problem on the test, okay? I can only ask one of these kinds of problems on the test because we got even tougher stuff tomorrow. But what are we going to do? Okay, just getting to that point is going to give you some significant points, right? The fact that you could convert it. Now, the next step is to actually take that and do what with it? Take it to the 10th power, which sounds absurd, but we're going to do it because we're crazy people. Root of 1/2 raised to the 10th power times the cosine of, what do I do to my angle? Times it by 10. What do you get when you multiply that by 10?
5 pi over 2.
Okay, so, yep, you guys are jumping ahead on it. Good. 10 pi over 4. And you said, I want to reduce the 10 pi over 4 to 5 pi over 2. Excellent, 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 excellent. Okay? Easy? Can you say where?
On the, how come it's pi over 4 and plus
So all we're doing is what they were saying is when we multiply this by 10, we get 10 pi over 4, and then we're going to use this space to reduce it. These two are the same, are they not?
Yeah.
So we just used, instead of rewriting it and then rewriting it again, we just went ahead and reduced it in that spot. This is not our final answer. We're just doing some work right here. Okay? So, yes.
We multiply it by 10. Oh, it's over 1.
Yes, good. So 10 over 1 times pi over 4. Yep, did you multiply the bottom by 10 too? Yep, don't multiply by 10 over 10. That's if we're finding like a common denominator or something. But in this situation, we just multiply the top by 10. Good, those are mistakes that people commonly make. So let's start to simplify this. This can't be our final answer. Square root means what power?
2.
1/2, right? So if you have a power of 1/2 and a power of 10, a power to a power, what do? Multiply. So you get 1/2 to what power then? The 5th power. Because the square root is the 1/2 power times the 10, that will give me 5. Times the cosine of, now here's the problem, and here's where we just need a little segment of this teaching to help you out here. We can't leave our angle expressed above 360 degrees or more than once around the circle. Is 5 pi over 2 more than once around the circle? It definitely is. So we want to figure out what other angle does it match with? Is it coterminal with? Okay, so let's see if we can figure that out. This is pi over 2. Agreed? So we're looking for 5 pi over 2. We have 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2. So 5 pi over 2 places us at the same spot as 90 degrees or pi over 2. Now here's another way to think about it if you don't, somebody didn't like that first hour. So I said, well, you could take 5 pi over 2 and you could subtract 360 degrees. Or what is 360 in radians? So you can subtract off that 2 pi. And if you do 5 pi over 2 minus the 4 pi over 2, we get pi over 2. So either way, sometimes people like the geometrical approach, sometimes people like that piece. So we've got it. Let's put it in there. Cosine of pi over 2 plus I sine of pi over 2. Yes?
The square root, normal square root, in exponent form, that's 1/2.
Yes. Yep. Good question. This is one of your answers. It's called the trigonometric form. We are also going to write the complex form. Okay? The complex form is easy. Once you get the trig form, complex form is easy. Watch. What is 1/2 to the 5th power? 1 to the 5th is 1. 2 to the 5th? 32. Good. Pi over 2, how many degrees? 90. Is cosine the x value or the y value? X. What's the x value up here at 90? 0. Sine of pi over 2. Y value, what's the y value of pi over 2? 1. So 1i. So when you look at this, you end up with 1/32 times 0 plus 1i. If you simply just distributed it, you would see you get I over 32, and that is complex form. So suppose that our friend Jordan was to actually multiply this out 10 times, and she said that would take her forever. She should come up with an answer of I over 32. Now, it would seem like it could be a little bit larger than that, right? But it turns out that there's so many things that cancel, you get I over 32. Okay? Which is kind of cool. And we did it to the 10th power. You're kind of tempted. You're like, I kind of like to try and multiply it out 10 times. Well, again, what if we do 100? So you've seen the foundation. That's the toughest problem. It only gets easier from there. Okay? Feel like you got a little bit of a grasp? Okay, you guide me through it then. We start with this one to the 20th power. Where do I start? R. Sound like pirates. Square root of?
1 plus square root of 3.
1 plus 3, which is? Dos. Spanish for 2. Then we find tangent of theta equals root of 3 over 1, which is the root of 3. Where is tangent positive? First and third. Is this the first or the third? First. Please inverse the root of 3 in your brain or on your calculator. What? Has Miss Netzer seen the video?
No, I don't.
Have you seen the Girl Scout cookie fail video?
So she totally just pissed on the back.
Well,
Show her.
is somebody in her flex? Oh, I got some track boys in her flex. They'll show you. They'll show you. It's a good time. It's a good time. So we got 60 degrees. What is it in radians? It is pi over 3. Excellent. So theta is equal to pi over 3. So therefore, my complex form, or my trigonometric form, is 2 times the cosine of pi over 3 plus I sine of pi over 3. Is that new? No, we did that the other day, right? So that's the first step. Once you do that, what do you want to do with this thing? To the 20th power. How do you do that? 2 to the 20th times the cosine of, what do you do to your angle? Multiply by 20. So Caitlin, if we multiply that by 20, all we have to do is just put a 20 in front of the pi. Plus I sine of 20 pi over 3. Can we leave it like that? Why not? Okay, so 20 pi over 3 is way too many times around that circle, right? So I take 20 pi over 3, and I subtract off 1 revolution. What's 1 revolution? 2 pi or 6 pi over 3. Good. What up, dog? I get 14 pi over 3. Too many, so what should I do? Subtract another 6 pi over 3, and I get 8 pi over 3. Subtract it again, and I get 2 pi over 3. Go ahead and write that down. So, yeah. Yeah. Yeah.
So when I was about to do, I did 2 to the 20th power, and I got.
Yes.
Is that okay?
If you want to take 2 to the 20th, you could do that. I find it to be unnecessary. Without a doubt, I think people would just express it as 2 to the 20th. Now, what's interesting is that sometimes this problem came up in on a worksheet one time, and people thought that I just decided to cross off the 0 when I went from that step to this step. See what I'm saying? Like, Mr. Getz, what did you do with the 0? I didn't realize you could just cross that off. Well, you understand how we got from that to that, right? It's about the number of revolutions. That's what we did. So this is what we call trig form. But I need complex form. So what I need to do is I need to determine the exact values of the cosine of 2 pi over 3 and the sine of 2 pi over 3. And it's part of what I love about this lesson in this unit is that you have to use all of your trigonometry skills. Because we spent the first unit determining the exact values of sine and cosine of 2 pi over 3. 2 pi over 3 is how many degrees? 120 degrees. Right there. What is that terminal point? Negative 1/2 and root of 3 over 2. So, which one is cosine, the x or the y? X. So I get negative 1/2 plus I roots of 3 over 2. That's complex form. Hi. No, so sometimes people would actually take the 2 to the 20th. They would actually, put that all in their calculator. But actually, you start to get numbers that are so large that you can't even write them down anymore. They're that large. Like your calculator doesn't have enough space for it, okay? The other thing is that the answer, the book, and some people, as they write an answer key, they wouldn't leave it like this. They would actually distribute the 2 to the 20th to each part, And I'm not asking you guys to do this, but they would distribute, and because there's a 2 on the bottom, they would get a negative 2 to the 19th. One of the 2's would go away, and it would be plus I times 2 to the 19th roots of 3 as well. So they would write their final answer like that. Now, I would accept that, but without a doubt, I think most kids just like to leave it like that.
We just look like that.
Yep, that's just fine.
That's constant.
Yep, that's just fine. Yep. Okay. Better than the first one, right? Kind of got the hang of it. So let's do the last one. So, all right, so let's be realistic. What do you want the time to be? I'm going to time us. Because she's saying it's taken her 15 months to do it, okay? So what do you think? Zizi, how much time? She's going for 3:30. Okay, are you ready? Okay, what do I start with?
Square the 1 squared plus negative 6 squared.
So good. I've got 1 squared is 1. I have negative 1 squared, which is 1. And as Kenny says, I have the root of 2. That's my R value. Good. So the tangent of theta this time is negative 1. In which quadrants is tangent negative? Second and the fourth. Why is it in the fourth, Aaron? Because if you were to graph it over 1 and down 1, it would be in the fourth quadrant. Good. If I inverse 1 on the calculator, I get 45, which makes this, as somebody already said, a 315-degree angle. In radians, 315 degrees. 7 pi over 4. So remember your conversion is, and that's on your notes as well, if you want to convert between degrees of radians, it's theta times pi divided by 180. That's your conversion that you're working with. Okay, that's my conversion. So if you need to do that, we have theta is 7 pi over 4. All right, so my I've got it. It's what do we got? We got root of 2 times the cosine of 7 pi over 4 plus I sine of 7 pi over 4. That is my trig form. What do you want to do with it? That's absurd, Aaron. How dare you? Taking the 100th power, who do you think we are? That's crazy people work right there. Okay, so square root of 2 to the 100th power times the cosine of what? 700 pi over 4? Plus I sine of, looks like Kenny already said, he said, I think 700 is divisible by 4. And it is. He got 175 pi. Oh, Rachel, tell us your thinking. How'd you come up with it?
Well, because it's going around like a lot of times, so you gotta subtract that off.
Yeah, let's show Rachel's methodology here. But first, we have 2 to the 1/2 to the 100th. So that's going to be 2 to the 50th. Good. Cosine of, and now Rachel says 175 pi. Look at her logic here. She says that this is pi, this is 0, and this is 2 pi. So she says 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, 7 pi. Notice how all the odd pi's end up over here? So 175 pi is going to be coterminal with just pi. Now, you could subtract off 2 pi over and over and over again if you want, but you're just going to get pi in the end. This is called what? Trig form. To end this problem, we want to put it in complex form. We have 2 to the 50th power times. Okay, so pi is how many degrees? 180. So what's the x value over at 180? -1. And what is the y value? So that goes away, and you get -2 to the 50th power. That is your complex form. I know I slowed you guys down a little bit. We're 350. We'll take it. I know I slowed you down. Now, again, to the 100th power, I mean, you got to stop and realize how impressive that is for a second. Now, let's be honest here, okay? Ava, when are you going to use that in real life? Wow, I got the finger wave. Absolutely never. I'm not going to lie to you guys. You're never going to use that. And in fact, you are investigating what is called the complex realm of mathematics. So if you're a math major in college, you might take real analysis, and some might take complex analysis. It's kind of a branch of mathematics that we're still learning and still studying. In fact, did you know that there's problems out there that we can't even figure out in mathematics to this day? When I was in college, I had a professor. He walked into class and he handed out a sheet of paper. And he said, here, try working on this. And we looked at it. When we went to the backside, it said, if you solve this, you pretty much will end up with $2 million in the Nobel Prize. And today, if you were able to solve it, you would end up with probably more like $10 million in Nobel Prize. Let me show you a little bit of what I'm thinking about. Miss Taylor, can you give me a 2-digit number that's even? 64. 64 is the sum of two numbers, okay? And they can be written as a sum of two primes. For example, I could write 33 plus 31. Do those add to 64?
Yeah.
But are they both prime? Nope. 35 plus 29, are they both prime? Nope, that one's not. I could go 37 plus 27, are those prime? No. 39 plus 25? No. 41 plus 23? Yeah, those are both prime, aren't they? In fact, every single even number that you can write down, you can see that it is the sum of two prime numbers, 13 plus 5. We know that this is true. We cannot find a single example in all of humanity where this is not true, yet we cannot prove it. Why? Because we cannot say anything intelligent about prime numbers. And it's like, should we try to say something intelligent about prime numbers? We should, because we've shown in mathematics that mathematics is always here and society is here. And what I mean is this, as mathematics progresses in its advancement, eventually reality catches up and finds a way to make use of it. And so we continue to pursue. But the search for prime numbers and its application has everything to do with our work here in the complex analysis. Has anybody ever seen the movie A Beautiful Mind? Come on, you've seen it? Good movie, is it not? It's a good movie. People are like, I would never watch it. It has to do with math people. Folks, it's a beautiful movie. It was one of the best movies of the year. One picture of the year back in the day. It's about a mathematician, and actually his pursuit within complex analysis. I take a glance at it, okay? Good job today, okay? Tomorrow is another tough one. And then after that, it gets easier for the rest of the year. Tomorrow's kind of like it, okay? It's kind of the pinnacle. And through it's the complex numbers, it's a doozy. Get ready. Hey.